Okay, here's part 3 of our science test review, and let's get right into it. We'll talk about matter. Why does it matter? So remember when we talked about matter, we said it's only 5% of the universe. Let's use my page marker, and we'll start with a little Halloween color. Why not? Why not? Put it there. We go. So again, we can put it there. We say it is. Line it up right. There we go. And so there we go. $5 foot long, 5% matter in the universe. That's it, 5%. That's all we have. We have to work with it, 5%. And the smallest particle of matter that constitutes an element, that makes an element, is the atom. Yes, there are smaller particles than the atom, but this is the smallest you can get to make anything that resembles an element, right? Because anything smaller, these subatomic particles that I'll talk about, don't make elements. You need the complete atom to do that. So here's our first atom we'll talk about. It's the lightest element in the universe. It's the lightest. Make sure you know that hydrogen is the lightest and is the most abundant. There's more hydrogen in the universe than any other element. Thing is, it's rare on Earth. It's only found in water, right? H2O, which we'll talk about shortly, right? So you need 2 hydrogen molecules and you need 1 oxygen. So here's a simple one. Clear this out. This is a basic hydrogen. As you can see, it has a nucleus and it only has a proton. That's it. It just has 1 proton in the nucleus. It has an orbital, 1 orbital, or which, it's supposed to be called a cloud, but we say orbital for now. And or shell, we can say shell, orbital, or ring, and it has 1 electron. So as you can see, the electron is negative. It's a negative charge the electron has, and the proton has a positive charge. And this electron is in its cloud. It's not circling the nucleus, it's appearing around the nucleus, and that's what's happening. That's why we call it in a cloud. But we'll talk about that in other videos. So this basic hydrogen element is just protium. Just protium. Now we can just say hydrogen. Okay, we'll clear that out. It's the lightest and most abundant element. And it's highly flammable. Hydrogen is highly flammable. Okay. So when they made the Hindenburg, if you remember the Hindenburg Zeppelin, it was filled with hydrogen. That's why they don't use hydrogen anymore in blimps or Zeppelins. They use helium. It's safer because helium is a noble gas. It's stable. It's not going to blow up. So again, I said there are smaller particles, those subatomic particles. So again, if we try to draw a hydrogen again, there's our proton. There's the electron. The electron and the proton, they are subatomic particles, right? Atomic particle will be the atom, and subatomic is below. Sub means below, means under. It's a Latin word. That's why we have subway, the subway, right? And there are even smaller particles. There are quarks. There are quarks. Quarks are inside protons, so that could be a proton, and they're inside neutrons, which we'll talk about. So in a proton, there would be 2 up quarks, looks like that, and in the neutron, there's 2 down quarks, but I'll go over that in a minute. And in the electron, there's nothing. There's nothing inside an electron as far as we know now. Don't know if there's anything in there now. Okay, so here's some isotopes of hydrogen. These are isotopes now. Bring up our thing in a minute on here. Okay, isotopes, right? So an isotope just means that there's an extra neutron in the element. In case here is hydrogen. So we have here, bring it over, deuterium. Deuterium has another neutron. See, hydrogen doesn't have a neutron, but when it gets a neutron and it still has that 1 electron, it's an isotope, deuterium. And deuterium is heavy water. It's used in nuclear reactors, heavy water, which we talked about in class. Tritium is highly radioactive. It has 2 neutrons, and it's very expensive, tritium. So as you can see here with protium, it has 1 proton, 1 neutron, and it has no protons, so the atomic weight is 1. right? The atomic number is 1. Atomic weight is 1. The atomic weight, you should remember, is just adding the protons and neutrons together. So if you add the protons and neutrons to deuterium, it's 2. So atomic weight is 2. Atomic number is 1. And there's tritium. So again, these are isotopes. Isotopes. So you don't see the isotopes or the ions on the periodic table. They're just different forms of the elements. All right, we'll clear that out. Moving it up here, we have helium. So what happens, Neely, as you see this, and this is the Bohr model. The reason why we call it the Bohr model is Niels Bohr created this model that we use just for class purposes. Let's change the color. Why not? Change it again here. So this is the Bohr model, and we just use it for teaching purposes. So we see this is the nucleus, and then around it we have its orbital or cloud. The proper thing to say is cloud. And the most you can get on this first ring or orbital or cloud is 2. You can only have 2 electrons. So remember, helium had a proton and an electron. Excuse me, hydrogen. So if another electron wants to join the party, here comes another electron. Now you have 2 electrons. And normally what you see is if you have 2 electrons, you'll have the same number of protons. Now the problem is, if you have 2 electrons and 2 protons, you need something holding the protons together because protons do not like each other. They have a positive charge. So there's a positive charge, there's a positive charge. They will not go near each other, right? They want to go away from each other. So the protons will go away from each other unless you have that neutron, and you need 2 neutrons for those 2 protons. So you see those neutrons right here. The neutrons are like babysitters. They're like glue. We're holding the protons together. So that's why helium has 2 protons and 2 neutrons to hold it together. And we'll talk about this force. It's called the strong force. The strong force is the strongest force there is. And when we talk about forces soon, we'll go over that again. Okay, so right now, if we see this, I said the maximum you can have in the first ring is 2. So if here comes another electron, if it wants to join the party, it can't. So you have to form another ring. Only 2 for the first one. So if we form another ring, here it is. Now we have 2 rings or two orbitals. So now we have lithium. And you can see what normally happens is if you have 3 electrons, you're going to have 3 protons. And if you have 3 protons, you need 3 neutrons. And this normally happens until you get into heavier elements. And once they get heavier, you're going to need an extra neutron. But for the most part now, just think of it as if you have, just count the electrons, and that'll be the number of protons. And again, the electrons are negative, protons are positive, and the neutrons have no charge. Now inside, we talked about this before, inside a proton you have 2 up quarks and 1 down quark. And in the neutron you have 2 down and 1 up. Generally like that. These quarks are, again, they're subatomic particles. They're in protons and neutrons. Nothing is in an electron, as we know. And remember, opposite charges in antimatter. Now, in antimatter, everything will be different. So let's look at it here. So if you had an electron in matter, it would have a negative charge, but in antimatter, it would be called a positron. A positron will have a positive charge. So a proton in matter has a positive charge, but an antiproton, that's all they call it, antiproton, will have a negative charge. And the neutrons, both neutrons, an antineutron and a neutron, just both have no charges. Now, we talked about antimatter before. They're trying to create it in CERN. CERN, it stands for the European Institute for Nuclear Research. I know that doesn't sound like CERN because CERN is a French word. But it's in Switzerland, and they're doing all kinds of research on the atomic level. And they have made antimatter, like I told you before. Bring the page up. There we go. Let's use blue. Why not? So they have created about 15 nanograms of this stuff, and they use penning traps. Remember, that's how they trap it. So because if antimatter and matter got together, there would be an explosion. 15 nanograms is really not much. It can't even heat up tea, like I said. Just to understand what a nanogram is the weight of a cell. So 15 nanograms will be 15 cells, and that's very, very small. And like I said before, if we made a gram of this stuff, which we haven't, it's very expensive, a lot of energy involved, we can create a nuclear bomb just from 15 grams of antimatter. So here's Switzerland in Europe. There it is. There's Switzerland. Here's Italy, France, and Germany. Here's the Alps. Just to give you a location of Switzerland. Okay, so let's look at molecules and compounds. All right. So first of all, you should know that compounds are molecules, right? All compounds are molecules, but not all molecules are compounds. So basically, when you have the same element, so right here we have 2 oxygen, right? And that's what's in air. Air has 2 oxygen molecules in it. That's why if we wanted to create water, if we had pure hydrogen, we just couldn't use air because there's 2 oxygen molecules. We need 1. So air has 2, so 2 oxygen molecules is a molecule, right? 2 of the same anything, 2 gold, 2 silver, 2 hydrogen, 2 helium, it's a molecule. But when you have different ones, like right here, we have 2 oxygen and 1 carbon, so we have carbon dioxide. And remember in science, di means 2, oxide means oxygen. And you can see we have 2 oxygen and 1 carbon right there. So a compound is the two different ones, and a molecule is 2 of the same. But again, a compound is a molecule. So it's just get your head through that one. Again, I'll just keep that up for a minute so you see it. If you have the same oxygen molecule, different ones, a compound. Okay, so and here's another picture of it. 2 oxygen atoms together, and then H2O, water. You can see that the hydrogen is much smaller than the oxygen. All right. And so here's the water. Its common name is water. That's what everyone says. Vata. I need some vata. Water, right? The chemical name is dihydrogen oxide. And by now it should be getting a little familiar for you. Di means 2. So we do have 2 hydrogen. And oxide does mean oxygen. So here it is. Here's the chemical formula, H2O. I think we all know that one. And the 2 means we have, and this is a subscript, it has 2 hydrogen, 1 oxygen. So, if you go into a store and ask for dihydrogen oxide, they probably will not know what you're talking about. So here's another, so again, this is a compound because it has 2 different elements. And sodium chloride, which you should know by now is salt, this is a compound. Sodium chloride is its chemical name, salt is its common name, and here's its formula, right? It has sodium, Na, and chlorine, right? And you get sodium chloride. And it's funny, these 2 things by itself, you do, chlorine by itself, you use it as diluted in pools. Sodium by itself is highly dangerous. You won't see it by itself in nature, but sodium, if you ate a piece of sodium itself, you will definitely burn from inside out. So do not attempt it if you can find it, but you will not find it. So now let's talk about density, mass, and volume. We did some experiments on this. Mass is how much matter is in an object, right? How much mass. It does not change. Here's that word intrinsic we used in class. Intrinsic does not change. Right there. Intrinsic. Weight is the force acting on an object due to gravity, right? So weight does change. Your weight will change depending on what planet you are on. Now, when we had a quiz before, I assumed you knew that the different planets, the different, what was bigger, what was smaller. So, you will definitely, so here's on Earth, the Earth is much bigger than Mars. So you will weigh different on the planets. Your mass will stay the same though. Your mass will be the same, but your weight will change because of gravity. Earth is much bigger than Mars. And in the last video, we looked at some of the comparisons on planets and moons. Now, to find your mass, this is something we'll do later on in the year, but we tend to just use weight most of the time when we're in classrooms. But what we need is you have to find your mass in newtons. Newton from Isaac Newton, right? And a newton is about 1 pound. 1 pound is about 4.4 newtons. It's actually more than that, right? It's a long number. It's 4.44822162 and so forth. But you just say about 4.4 newtons is 1 pound. So to find your mass, you really need to find how many newtons you are first. So, for example, if you were 150 pounds, and again, we're going to do this later on in the year, you would be about 667 newtons, right? And what you will do then to find your mass is you will take 667 and you divide it by the gravity, the force of gravity on Earth in meters. And again, your answer would be, you would be about 68 kilograms. That's your mass. So we tend just to use weight. We in class we're using weight. We're using a triple beam and we're getting the weight of an object. We're not actually getting its true mass. But we'll do that later on in the year. So this is just, again, what we will do later on, just to put it in your brain, and when we come across it, it may be familiar with you. All right, I'll leave that up for 1, 2, 3 seconds. You can always rewind the tape. So once we have that, let's look at volume. So volume is, again, what a substance occupies, and it's in its 3D space. It's measured in cubics. In other words, it's cubed, right? So if we had let's draw something here. We have the page marker. A different one. Let's use this color for now. We haven't used that. I don't think we used it at all. So if we have, let's say we have a rectangular prism here, and, well, that's 3D object, right? The volume is what it can fill up. That's the volume. So you can have particles in here, and that could be its amount of its mass. You can have the same volume, let's say, and it's packed more tightly. And if it's packed more tightly, you're going to get density, which is the next thing we'll talk about. So mass is how much matter it has. You can see there's much more matter in this one. And volume is how much space it occupies. And then we have density. Now, to get volume, we used Archimedes' principle, or displacement. Archimedes lived a long time ago, at the time of Aristotle. He was a scientist. And what happens with this, and we did this in class, if you put an object in water, the water will be displaced. It will rise up and be displaced. And the object, and it has to be completely submerged. And the volume, if you want to find the volume, it's just the water that it was displaced. So you can see this was the water line here. Right here, and we did this experiment right there. And as we put the object in, the water rose up and came into this cup. And right here, that will be its volume. And that's what Archimedes found out over 2,000 years ago. So if we weigh something and then we use getting the mass formula, we can get its mass. We can put an object in water and get its volume, and then we can get its density just from the density formula. So the density measures a substance mass per cubic volume, right? So how much of it is packed in based on its volume is its density. So you can see here they have the same volume, but you can see there's low density here. They're not as packed in as this object, and it would be much heavier. Okay, and the same thing if, let's say, you had a pound of gold, or if you had a pound of bricks. If you had a pound of bricks, here's our scale. That's our beam, let's say. If you had a pound of gold, right, there's the pound of gold, let's say, and then you had a pound of, let's say, feathers, right? Well, it would be, you need much more volume of feathers to equal out that little tiny pound of gold, because gold is much more dense than the feathers. Now, gold is very dense. It's really dense. but it's not the most dense object there is. There are more objects that are denser than gold, and this should be most objects, not most are. It's a nice little word here. Gold is there's objects denser like platinum. Platinum is much more denser. Well, actually, not much more denser. But the most dense substance is osmium. Osmium is very dense. So gold, for example, has a density about 19.3 grams centimeters cubed, and osmium is about 22.34 grams centimeters cubed. So osmium is much more dense. The matter, the particles are packed in much more densely than gold. But gold is much more valuable than osmium, by the way. So being more dense and being more valuable are two different things. Okay. And there's a picture of osmium. Very silvery looking thing, but very dense. Now, just to go over, let's make sure that we have, here's the density formula. Let me write that down. And so density equals mass divided by volume. And this is in terms of density. The word in terms of, we need to know. We had it on a quiz, but I didn't count it as a question yet until we get used to it. So if I want this in terms of volume, that means you want the volume by itself. And remember, you can either multiply up or divide down. Remember that. Multiply up, divide down. So in this case, you would have to divide down. So it will be mass divided by density will give us volume. And if I wanted it in terms of mass, now we can multiply up. Multiply up, divide down. Try to remember that up. Multiply up, divide down. And we'll do this again and again until you get used to it. All right. And the last thing we should talk about is glass making. We talked about how we make glass. There's a lot of ingredients in it, but the main ingredients is sand. So you heat up sand. You need a lot of temperature to heat up sand. And if you wanted to make red glass back in the days, you used gold. That's why red glass is very expensive. Copper for blue. And the Egyptians used copper and cobalt and got a really deep, rich blue for glass making. All right, so that's the review for the test. There's a lot of things we went over. And so just you can either study the two quizzes and you can go over this video. All right, good job.